Welcome everyone for the last row before the summer break. I'm very happy to have Shimrit Shtern here. She's senior lecturer at the Technion Israel Institute of Technology, where she also received her PhD. And then afterwards, she did a postdoc at Operation Research Center at MIT. And her research is focused on optimization and uncertainty from a theoretical and application point of view, and also for development and convergence analysis of first-order methods. And I'm very happy to have her here today. Please, Shimrit.
Thank you, and thank you, Yanis and Reza, for inviting me. So I'm going to talk today about smooth uncertainty sets. This is joint work with Noam Goldberg and Michael Poss. And also I will show some things from another work I did with Noam Goldberg and Mark Langer from Indiana. As just examples for this talk. So just a bit of motivation. So we can look at two different cities at the same time of day, and we would imagine if the cities are close together that the temperature would be similar. Or we could look at the certain road at sequential hours in the day, and we would assume that the traffic congestion would not be as well too much different from each other. Or we can look at biological condition in the brain. So here we have a biomarker indicating the levels of oxygen in the brain, and what is the red part is the tumor. And first we would assume that the oxygen levels would not differ if you move slightly inside the brain too much. And these are all examples of situation where we have an object which has some uncertainty. So for instance, the town, which has the temperature, or the road, which has the congestion, or the brain, which has the oxygen level. And we say that objects which are similar to each other, we expect them to have similar values for the realization of this uncertainty. So what is similar object? Similar can be similar in space, close together, time, or in some other feature space, whatever feature space we can imagine. And to model this uncertainty in a good way, we would want a model that limits this distance between the realizations of the uncertainty of these similar objects. And there's also a question, what happens if there is such a kind of dependence between these objects, but we ignore it? And so I hope to answer these questions in this talk. And in order to give a bit more of kind of a real-life motivation, I want to go to an application that we also will talk about later, radiosensitivity of voxels in radiotherapy. So basically, in radiotherapy, we want to radiate a tumor, and the effectiveness of our radiation depends on biological conditions such as oxygen level, and we measure it by something called radiosensitivity. And here we took actual data from work by Clark et al. For a specific patient. And we look at two voxels. Voxels are just three-dimensional pixels, in this case of a brain. And we measure the distance between the voxels versus the measured distance between the radiosensitivity. And so what we saw here, that when the voxels are very close together, for instance, they are adjacent voxels, then the maximal difference in radiosensitivity was about 0.02. And when we increased the distance between the voxels up to 10, more or less, this distance between radiosensitivity also increased. So what we saw visually before actually happens. Above a distance of 10, the geometry of the 2 more actually takes into effect, and so that's why we see these jumps here. But until then, we can kind of see that this bound on the distance between radio sensitivities, which is a function of the distance between the voxels. So this is more of a real-life motivations for what we're doing. Another, if we can see, we have the traffic map for Boston area at 9 a.m. on a Monday. And we see congestion. So reds are slow and yellow is slightly less slow and green is fast. But for different road segments that are adjacent to each other, we would expect that the differences of the congestion would not be significantly large, right? So if we now take each road segment and give it a letter here, we can say, oh, so if it's red and yellow, that means we can limit the difference between the congestion here by a certain amount, and so on between B and C and D, and so on. But this doesn't need to be only for adjacent segments of the road. This we can also look at, for instance, F, which is a very congested road, and J, which is also a very congested road, and say they have same features. They're both going into kind of Cambridge. So we expect both of them to be busy at the same time of day. So we can now have edges between segments of roads that we think are connected in some way. So it's not necessarily only by location, maybe other features as well. And we have parameters gamma for each of these pairs of road segments that will limit how far the congestion of these segments would be from each other. So looking at this kind of graph, we can call this an uncertainty graph. And from this uncertainty graph, we can build an uncertainty set. So the uncertainty set is built as follows. First of all, we assume that it has n vertices. Okay, so let's just number 1 to n instead of the letters above. And we have a nominal value for each of these vertices of the uncertainty. We allow to go up and down from this value by gamma II in this case for the ith element of this vector. So this will create a box, a multidimensional box uncertainty. But on top of that, we also limit the absolute distance between 2 different uncertainty elements I and j, and they're limited in absolute value by gamma ij, which is some function of their similarity, let's say, okay? And we might not even do it for all pairs ij. We can decide what pairs are connected or not connected. We can always think of the pairs that are not connected and the pairs that we give gamma ij to be infinity, okay? And this is what we define as a smooth uncertainty set, and we call it smooth because we kind of are trying to depict continuity, if it's a continuity along time or a long space. And now we're looking at this uncertain optimization problem, okay, where delta depicts the uncertainty, and we want to solve the robust problem where we want the constraints to be satisfied for all delta in our new smooth uncertainty set. I want to mention that x and y here can be in some set z. Z can include, for instance, integrality constraints. So we were not restricting ourselves right now to only linear problems, but actually linear mixed integer problems, okay? And this talk will touch 3 points. One is giving some probabilistic guarantees for this uncertainty set, meaning that what can we say if delta is actually a random variable? What can we say about the solutions of this robust problem in terms of the random variable? We will talk about tractability. So this uncertainty set may have a large number of constraints because it depends on the number of edges, and the number of edges can be large. And we show a compact reformulation column generation algorithm to solve this problem. And we, like, throughout the talk, I also would give examples to hopefully convince you of both the tractability and the fact that this uncertainty set alleviates the conservatism that we get with box uncertainty, while still having a nice polyhedral set. So we'll start with the probabilistic guarantees, and for that we need some assumptions. So let's assume the delta is a random variable with expected value 0 and covariance matrix given by sigma. And without loss of generality, you can also assume the diagonal of sigma is all ones. And in this case, we can actually show the following. If we construct the smooth uncertainty set in this specific way, we set delta hat to 0, so the nominal value 0. And the gamma ij, I depict them with epsilon here, we set them as these values, where we have square root of n divided by p, where p is the probability that we want to ensure of not violating more than p. And the eij are vectors, which if I equals today just the ith basic vector in the standard basis in Rn, and if its I is not equal to j, it's just the difference between the ei vector and the ej vector. And in this case, we will have a guarantee that the probability of delta, the random variable being in this uncertainty set, will be greater or equal to 1 minus p. So I have this superscript E, or calligraphic E or epsilon here, because the proof of this actually comes from the fact that we are using ellipsoids. So what we do is we can actually construct an ellipsoid uncertainty set that is derived from multivariate Chebyshev, and then find gamma for which our smooth uncertainty set encloses this ellipsoid, but we find the smallest gamma that does that, and that's how we derived our gamma. And of course, the proposition here guarantees that any xy, which is a solution to the robust problem, is also feasible for some realization of delta with probability of at least 1 minus p, because that will be greater or equal than the probability of being inside the set. So this was the first result, and what we didn't like about this result is, of course, that depends on n, which is the size of the or dimension of the uncertainty. But of course, we know that we can also treat the case for a single constraint and get nicer results. So for a single constraint, so I just omitted the index I from the constraint parameters, and we look at all xy which are feasible for the robust constraint. And in this case, we can set gamma like this. So we have a nicer gamma, it doesn't depend on n. We have also -1 here. So instead of square root of n divided by p, we have 1 divided by p minus 1. And this guarantees that xy that belongs to this nice set is satisfied the constraints for a random delta with probability of 1 minus p. And this is actually an extension of the results by Bertzimus, Den Eltok, and Polyhedral from 2021, their paper about deriving probabilistic guarantees. And the main difference here is if we use their approach, we would get here something that depends on the maximal eigenvalue of sigma. And so we have a more refined version here where it depends on this norm. Of course, it's better than the other constraints if we have multiple, the other, results that we just showed. If we have multiple constraints, only if the number of constraints we have is smaller than the number of uncertain variables, because then we can use the union bound and show this inequality. And this is for general probability distribution with knowledge about mu and sigma. if we additionally assume that we have a normal distribution, of course, we can get a much better result. Specifically, we can have two constructions of our uncertainty set, one dependent on the chi-square distribution and one dependent on the normal distribution. The one dependent on the chi-square distribution takes the 1 minus p percentile of the chi-square distribution with n degrees of freedom. And it's actually, again, derived from using the distribution of the Mahalanobis distance, which is basically the distribution of the uncertainty times sigma minus 1 times the uncertainty again. And this we know is distributed according to chi-square. So, and we again build our smooth uncertainty set as enclosing polytope for the ellipsoid derived by this Mahalanobis distance, ellipsoidal uncertainty. And the second case, we just take the fact that for each constraint in the uncertainty set, we have a variable that is normally distributed. And if we want all the constraints to be satisfied, we need to divide it by the number of constraints in the uncertainty set, which is 2 times the number of edges plus n. Surprisingly, though, although in the second case, we take a percentile, a much larger percentile than in the first case, it is actually results in a smaller uncertainty set. So beta is actually smaller for the second case if p is smaller than 0.2. So for small enough guarantees, or for actually good guarantees, we actually would want to use the second and not the first result. And just to give you some sense of what kind of results we get, so we took a very simple example with dimension 5. The covariance matrix is a full matrix, meaning we look at the full graph, where the correlation between I and j is given by a rho to the power of I minus j. So if you can think of it as one dimension, and I is the location, and I minus j is the distance between location I and location j. And we want to guarantee something with probability p 0.01. And what we have here is, in red, is the ellipsoid uncertainty set we get from the Mahalanobis distance that gets this guarantee of 1 minus p. The pink is the smooth uncertainty set with chi-square, which is basically a bounding smooth uncertainty set for this ellipsoid. The blue is, of course, the box uncertainty set that bounds this ellipsoid. And the green is the uncertainty set that we constructed from the normal distribution. This is here for rho equals 0.2. And of course, we have a 5-dimensional uncertainty set. Here it's the projection on the first and second dimensions, just so we can look at it. And what happens when rho is increased? When rho is increased, we see everything kind of shrinks. And specifically, this uncertainty set shrinks. But in both cases, the green uncertainty set, which is derived from the Z, is better than the pink that is derived from the chi-square. So this is also true for the general probability guarantees that we get, that as rho increases, as the correlation between uncertainty increases, then we'll get smaller and smaller uncertainties. So I hope this convinced you that we get some probabilistic guarantees from using this uncertainty set, but we now need to solve the problem. So the question is, how do we solve the problem? So one can say, okay, the smooth uncertainty set is polyhedral, so we can use reformulation and get an LP or MILP, okay? And so we still are in the same kind of type of problem. But actually, because the number of constraints in the uncertainty set can be large, it depends on the number of edges, and this may be very prohibitive. So what we did is found special structures for the constraints for which we can get a compact formulation. we actually showed that in other cases, finding the worst case for any constraints is the same as solving a mean cost flow problem on the graph that we know can be done efficiently. And so this of course can give rise to row generation algorithms and so on. And we also constructed column generation algorithm for the case where X and Y are continuous that we can use in order to find a solution for the robust problem, where of course this column generation can also be embedded as part of some branch bound scheme if you have mixed integer variables. So I will talk mainly about the first point, and hopefully I'll get also to the third point. And the second point I will not talk about in this talk.
Shimrit, there's a question in the chat.
Yes, yeah.
What do you mean when you say an uncertainty set is better than another one?
I'm saying, so that is actually a very good question. Better, you can think of it as smaller or not as conservative, but you can also think of it as getting better out of sample results. So it depends on if you have probabilistic or don't have probabilistic assumption about the underlying uncertainty. Okay.
Yep.
So in just to talk about reformulations, let's consider constraints that just a single constraint. So I omit the index I, and I look at the coefficients of the deltas. Okay, and I'm going to kind of divide them into groups. One kind of index set that I want to talk about is an index set where all the coefficients of the deltas are always non-negative. And I call this group S plus. And analogously, we can have S minus, the coefficients that are always non-positive. I also define S plus plus as S plus minus S minus. What does that mean? That means that all the indexes in S plus, all the indexes that have always non-negative coefficients, but for some X and Y, they might have a positive coefficient. That's S plus plus, and S minus minus is similarly like the opposite S minus minus S plus. So now we can classify constraints based on these sets, and we will talk about how to reformulate for specific types of constraints the problem. So the first one that we are going to talk about is the one that S plus actually has all the indexes in it, okay, 1 to n. And an example for this problem is the robust shortest path. So just to remind you what the robust shortest path is. So we have a directed graph. It's not necessarily the uncertain graph. It can be a completely different graph, okay? And in this graph, we have n arcs, okay? So we say that each arc has a length, which nominal lengths we denote by CA. And the uncertain objective is basically finding the minimum path from some vertex to another at a minimal cost. Well, cost is minimal length of path. And delta A is the uncertainty of the length. Okay, so it's something that multiplies the nominal length. And of course, the nominal solution is 1. It's exactly the average or the nominal, but it can go down or up. It can be higher or lower than that average. And the set X here, we don't have a Y here, but the set X here denotes all possible paths from the source node to the destination node. And here, if we look at the coefficients of delta A, it's CA times XA. XA is a binary, it's either 0 or 1, and CA is a length, so it's non-negative. So of course, all the coefficients are non-negative. So this is kind of an example where we have this kind of structure of a constraint. Here it's the objective, but we know that objective and constraints in robust optimization can be treated similarly. So the key elements of finding a compact reformulation for this problem, for this type of constraint, is the fact that we can compute the projections of the smooth uncertainty set on the J dimensions very easily. They, of course, are given by a segment because we have a convex uncertainty set. So projecting it onto one dimension will always give us a segment. But the segments can be computed efficiently in pre-process. So once we have the uncertainty set, we can compute these upper and lower bounds on each dimension. And the robust constraint is just equivalent of plugging in the upper bound for each index. So before I get into why this is true, what does it mean for the shortest path problem? So the shortest path problem, we know that it's an integer problem, but because of a TUM kind of constraints, we can actually relax the integer constraints and solve it in polynomial time. If we use an ellipsoidal uncertainty set, for instance, we would get a nonlinear binary problem, okay, in X, that is not easy generally to solve. There are algorithms, and I'm going to talk about numerical experiments. I'm going to show an algorithm that was constructed to solve these kind of problems, but they're much harder and take more time. Whereas the smooth uncertainty sets result in exactly the same structure of problem, meaning we can also solve it in polynomial time as the original problem. And so there are two questions here. How can we actually find these projections easily in pre-processing? And why does that admit this result? So first, let's start with the how. And I urge you to not read the lemma, but actually look at the nice illustrations that I have here. So we start with three components, J, L, and K, okay, of the uncertainty. And we build the original bounds for each of them, adding gamma and subtracting gamma, JJ, gamma LL, and gamma KK. So this is our initial bounds on each of them. Now we remember that we have a graph, and in the graph we can compute a shortest distance between each element to each element, each vertex to each vertex. And let's say the shortest distance, we can compute it in advance, and it of course depends on the gamma values, but we denote it by dist, okay? So now we know that the upper bound of J cannot be more than dist Lj from the upper bound on L, and the same for K. And the lower bound cannot be too far than this Lj from the lower bound here of L and K. So if we show these lines, this intersection will give us a new bounds, lower and upper bounds on J. And this is exactly the projection. And more than that, not only that we can compute this projection, if we take all the lower bounds and put them into a vector, this vector actually belongs to the smooth uncertainty set. And also, if we take all the upper bounds and put them into a vector, this also is an element of the uncertainty set. So because this upper bound is an element of the uncertainty set, and obviously if all the coefficients are non-negative, we want all of them to be as large as possible, then we get that choosing delta equal delta bar will give us this result. So it's kind of the same thing as we get for a box, but here we don't have a box. And just to illustrate this example for the shortest path, we looked at real Chicago data that was used by Chassain, Doka, and Gurek that also provided us with this data very graciously. And we compared with the ellipsoid uncertainty set, and that for which they solved the problem using their dedicated algorithm. And for the smooth uncertainty set, we considered two constructions that are based on basically the data. So S is a scenario or a data point. And so for each delta, we have the value for a specific scenario. And in our first construction, again, it's easier if I explain what we did. We took gamma to be somewhere between the mean distance of two points and the mean as in MEAN, and the max distance between those points. So if lambda is equal 1, it's actually the maximum distance. If the lambda is equal 0, is the mean distance. And if lambda is between them, then we have some convex combination of the mean and the max. And the same for each of the vertices separately. And we use this because that's what they did in their paper for constructing a box. So we can kind of extend the construction of a box for our smooth uncertainty set. So what we see here is the red is the smooth uncertainty set when we set lambda equals 1 and lambda tag we changed. So these are the values of lambda tag. We have the box, which is red, in which we don't have lambda tag. Lambda tag, you can think of it as infinity. And we only have the box, so we only have lambda. And so what we have here is for different lambdas. And the black is the ellipsoid uncertainty set with different sizes of ellipsoids. And so this is the in sample, and what we see here is the out of sample. And we can see that, of course, we get a better, by tuning one parameter, in our case, lambda tag, we can get a better result out of sample than both cases. But this was not a very intuitive construction of the smooth uncertainty sets, for us at least. And we looked at a construction which more fits the way we derive the probabilistic guarantees. So in this case, we have gamma, which is a multiplier of this norm that we introduced before. And we said just lambda tag equals 0.8 lambda. So we have the size of the box, which is determined by lambda, and lambda tag, which is always 0.8 lambda. And here we also build the box according to this. So if we say in sample, the box using this construction is worse than using the previous construction, but actually the out of sample is much better for the box and also for the smooth uncertainty set, and still we get a better result using the smooth uncertainty set. Okay, so not only are we better than the ellipsoid concerning runtimes, okay, we solve in polynomial time versus we need a dedicated algorithm that takes much, much longer. We can actually have comparable results to the ellipsoid. Sorry. So this was the first case in which all coefficients were non-negative. The second case for which we have a compact reformulation is the case where S++ has one element and all the other elements are S-. This means that one coefficient is non-negative and could be positive, and all the others are non-positive. Again, we want motivating example. Why do we care about these kind of constraints? And we have two motivating examples, but I'm going to talk about actually the example I talked about already, the robust radiotherapy planning. So again, radiotherapy planning, we have a patient, he is radiated by a machine that can turn and can radiate from different angles. So given that the angles are fixed, we need to decide on the intensity of the rays that come from each angle. To this point, we take the area that we want to treat and partition it into three-dimensional voxels and determine the intensity via the vector x. The dose in each voxel is determined by some matrix D, which we call an influence matrix, that multiplies this intensity vector. And the effectiveness of the dose is measured by the radiosensitivity coefficients. So if the dose is the physical dose that arrives at a certain voxel, when we multiply it by the delta, we get the biological dose. And the biological dose is the actual effective dose that the voxel gets. And this is how we want to measure the dose. But delta is very uncertain because we need to translate imaging data in order to derive it. And there is a constraint in this problem that says that the biological dose of two voxels cannot be too different from each other. And this is called an homogeneity constraint. Okay, this is how they measured it clinically. And as we can see, we have two delta coefficients. One is positive and one is negative. So this fits our problem. actually a degenerate case of our problem because we only have 2 non-zero coefficients. So this is just to motivate this case. And in this case, we can show that the robust constraint can be reformulated using at most additional n-1 linear constraints and no additional variables. Okay, so before we didn't have any additional variables, any additional constraints. Here we need n-1 additional constraints. And again, to illustrate why this is true, I will show, again, ignore the proposition. Let's see it via the image. So we start with these bounds on each of the uncertainties. These are the bounds, the projected bounds. Now, additionally, we have this distance between J and L. And we know that if we want J has a non-negative and possibly
I think she got disconnected.
Yeah, let's wait. I hope she comes back.
Can you see? Okay. Okay, so sorry. So since J has a non-negative and sometimes positive, we want it to be as large as possible, let's say. But then the other ones we want to be as low as possible. And but they can't be too far from the value of delta J. So if we set delta J to be in its upper bound, we know that delta A can, the lowest value it can get is exactly this upper bound minus this JL. And the same for K. So this is the first point we considered. So for the value of J that is its upper bound, these are the lowest values of L and K we can get. And this is the value of the constraints. Now we can change the value of delta J. So what happens if we lower the value of delta J? Okay, so we can shift it until the point where one of the other coefficients get its lower bound. Then we need to stop because we can't decrease this coefficient anymore. So let's say we stop here. We can still reduce delta J, but now only delta K will be reduced with it. And that will give us another linear function. So in general, if we have n-1 coefficients that are non-positive, we will have a total of n points that we will need to consider. Okay, so these are the realizations and we know how to compute them. And now we just have each of these realizations as a possibility for the uncertain value of delta. So total of n constraints, which means the additional n-1 constraint to the original uncertain constraint. Okay, because we know that the optimal solution must be in one of these breaking points or in the edges of the cell. So just to show why this is important, so here we depict in the radiotherapy example, what happens if we use a box uncertainty set versus this kind of smooth uncertainty set. So here we looked at several smooth uncertainty sets. Doesn't really matter because all of them actually perform better. They achieve a lower homogeneity value with a higher physical dose than either the nominal solution and the robust box solution. And just to show you more vividly, so here we see the dose on the brain. And the red spot is places with higher dose. The tumor here is in the center. So this is the area that we actually want to get enough dose to. And we get more or less the same dose in the tumor here. But as we can see, both for the nominal and the box case, we get what we call hotspots, higher dose values outside the tumor on healthy tissue, which is of course something we don't want. And smooth uncertainty set actually allows us to get smaller values here outside to get the same dose inside. So it's actually does get better results in the sense that it gets a better treatment here. Finally, I think I still have like 10 minutes, right? Slightly less. I will talk briefly about the column column generating algorithm for solving the problem for the case that we have a lot of constraints and a lot of edges, and the constraints are not of a specific structure. So this is our problem, and we can technically write our uncertainty set as a linear constraints, inequality constraints with A and B. So this is a more general column generation algorithm. And this is our Z. Here we assumed it's linear for simplicity. Okay, so here we assume that X and Y are continuous. If we dualize these variables, we have here a sum on the number of constraints, which in our case is the number of edges plus the number of vertices. So we can only take some of the edges instead of all of the edges. Okay, each edge defines two constraints. We can take some of the edges. And of course, add more alphas by looking at the dual problem and seeing if this constraint is satisfied for a specific L. If it's not satisfied, we will add this alpha L. If it is satisfied, we don't need to add this alpha. And do it until all constraints are satisfied. So this is a very standard column generation algorithm. But in our case, how can we choose what is the initial L's that we pick here for the column generation algorithm? And because we have a graph and we want to kind of take into account all the distances in the graph, a very natural way is to take the shortest path tree rooted as the center of the graph as our initial set L. And this actually worked pretty well. So we looked at a very specific example. So a two-stage example with linear decision rules, where we have a multi-location transportation problem. We have demand in multiple retailers. They have a base stock that they need to re-up at the end of the period. And once they get the demand, they can replenish it from their own stock or by transshipping stocks from other retailers. So this is a standard transshipping problem. And we took the setting from Heretzer and UC Sun from 2006 with N retailers. So the here and now decision is what are the inventory level of each retailer, and the wait and see are the transshipment amounts that we assumed that we depicted as linear decision rules. We took 10 random instances for each N, and what we should see here is the mean. We ran it on a server, so we allowed each of the methods to use at most 30 CPUs. And we compared 3 different types of methods. One is the dualization, so reformulation with all the constraints and all the variables. The second one is the cut generation algorithm, in which we add constraints, okay, realization of the uncertainties that are the most violating for each constraint. And the third one is our column generation algorithm. So this is for small n's, and we can see that the column generation algorithm matches the dualization both in time and doesn't show here memory consumption, but also had very low memory consumption, where the cut generation was very slow in comparison. So when we move forward, we only looked at bigger n's up to 100. And the dualization, the problem with it, as we know, that it uses more and more memory. So as we increase the number of retailers, the memory consumption grows larger. Well, the column generation actually used a lot less memory. As we can see, generated less variables Okay, so this is in thousands. Okay, so this is 6 million variables. Just so it will be in the same, the 400 it's 6 million variables. And it took more or less the same time, even slightly less time because of parallelization. So this shows that this column generation algorithm is a viable alternative for dualization, especially for very large problems, and does not take actually that long to solve. So just to summarize everything, so we introduced smooth uncertainty sets, which is a new polyhedral uncertainty set that tries to capture the dependence between uncertain elements, and it tries to alleviate the conservatism of the box while providing probabilistic guarantees and resulting in practically tractable, robust problem, either by compact reformulation or algorithms to solve it. Thank you. So as I said, this is a working paper with Noam and Michael, which we hope to submit soon. And the radiotherapy examples are from recently published paper with Noam Goldberg and Mark Langer.